Welcome to Convocation today. Our speakers today are faculty members from the natural sciences and mathematics division here at Snow College. Dr. Larry Smith teaches physics. He also runs the astronomy lab, and he teaches math as well. And I'm sure that there are other things that you do. Oh, he's the honors director. He's one of the honors director for the program here, the honors program here at Snow College. Professor Jonathan Tyler, also teaches math here at Snow College. And both of them are very interested in music. Okay, so these two interests in mathematics and in music, and they found a way to kind of bring them together and show you how they relate to each other. So we're really excited to have them here with us today. Please welcome Professors Smith and Tyler.
Thank you. It's an honor to be here. I am Professor Tyler. We are going to talk about some of the remarkable things that we have learned over the past few years in making comparisons with mathematics and music. For several years, Larry has taught an introductory physics course specifically towards music majors. And we came up with an idea of creating a whole new physics course specifically called the Science of Music. And we've broadened it to be accessible to all students as a general education course, not just as a music majors course. And we want to share with you some of the, again, really incredible things that we have learned as we have prepared and taught this course. Among those things is our discovery that musicians don't have to be expert mathematicians to create beautiful music. But understanding the basic ideas of how mathematics can enhance music and complement our understanding can be very useful. Our textbook for this course is the source of all that we've learned about over the past 3 years as we've dived down a very deep rabbit hole. Our textbook is an open educational resource book. It's freely available on the web, where students get to learn through simulations. They get to get their hands dirty and actually be active part of the learning, seeing how things change and how their interaction with the environment can cause certain changes. In researching and preparing for class about 3 years ago, we came across a paragraph in the textbook that did not make sense to us. And again, this opened up a very deep 3-year journey of exploration and trying to understand what was being said. And Larry has been able to reach out to the textbook author to make clarifications, and he has been very good about making adjustments and helping us to understand things as we've gone through them. But we would like to make one thing very clear about all of this. We are not experts, and we have not discovered anything new per se, but we have developed a better understanding, and we hope to pass that on to our students and make this a much better experience for them. A few things that we're going to go through. We're going to discuss how the logarithm, a very scary mathematical concept, can help us understand better musical frequencies and pitch. And we'll observe how ratios of different frequencies make up different musical intervals and how they can be used to create musical scales or temperaments. And we like to emphasize the visual understanding of these using different graphs and creations that we have made to illustrate how the different tuning systems go together. And we have, of course, observed that music has evolved and changed quite a bit over time. And we want to talk about how some of those things have changed throughout history and to what we experience in the present day. And again, we want to focus on this idea that having a basic understanding of the mathematics can enhance our enjoyment of music. When we talk about sound waves, there are some very useful and important interrelated properties. If we take a picture of a wave at any instant in time, then we can observe the distance between two successive wave crests. And we measure this distance and call it the wavelength. The wavelength is a distance measurement, and we use the Greek letter lambda to represent that wavelength as a measurement. If instead of looking at a specific snapshot in time, we look at one individual point on a wave, as time evolves and as that point moves up and down or back and forth, we observe the period of the wave, the time that it takes to go through one complete wave cycle. The period of a wave is most closely related to its frequency. They are inverse relationships. So if we know the time that it takes for one wave to pass by us, then we can compute what the frequency of that wave is. To measure the speed of any given object, we compute the distance that it has traveled and divide it by the amount of time that it took to travel that distance. Likewise, we can compute the speed of a wave as it moves by taking the wavelength and dividing it by the period. And using this reciprocal relationship between the period and the frequency, we can observe a very simple and beautiful and very critical equation that the speed of a wave is equal to the product of the wavelength and the frequency. In terms of music, most musical instruments are going to create not just one single pure tone, but they will create multiple pure tones all at the same time. We call these different tones harmonics. The very top picture you see here is the lowest harmonic, or the fundamental. We call this the fundamental frequency, and we associate the pitch of a musical tone with that fundamental frequency. It is the basic jump rope of the vibration of a string. You can consider these pictures as if they were the vibrations of a string that is fixed at both ends, such as in a guitar or violin or a harp. The second harmonic is going to still have the string fixed at both ends, but we can also create a node or a fixed position in the center of the string. And this gives us a double Dutch picture of a jump rope. We can get our higher harmonics as well, and we observe a very important relationship that all of the harmonics are whole number multiples of the fundamental frequency. And I'm going to play you a sound clip here of a fundamental tone and 7 harmonics of that. So our first tone will be rather low at about 150 hertz. And then the second harmonic will be twice that, the third harmonic will be twice that, and so on. So we can ascribe to each one of these harmonics their own individual note names. That fundamental frequency on the far left there would be one particular note. The second harmonic would be another note, a different note, and it is specifically 1 octave above the fundamental frequency. The third harmonic and fourth harmonic would all represent their own individual note values as well. We can observe that specific ratios of these harmonics or of these frequencies produce different musical intervals. The 2-to-1 ratio between the frequencies of two tones produces the interval of the octave. The 3-to-2 ratio of harmonic intervals gives us the musical interval called the perfect fifth. The fourth is the interval from 4 to 3. The major third, 5 to 4, and the minor third, 6 to 5. Now these low number common ratios can be observed elsewhere in our harmonic series. So the 2-to-1 ratio of the octave can also be observed here by finding 2 other harmonics that are also in that 2-to-1 ratio. 16 to 8 also reduces down to 2-to-1. 6 to 3 would also reduce down to the 2-to-1 ratio. Other musical intervals can also be found. For example, the perfect fifth has the simplest ratio of 3 to 2, but any other combination in that ratio is also going to be the interval of a perfect fifth. So 12 to 8 would also be a distance of a perfect fifth. Musicians will give different symbols to all of these different intervals. The octave, the fifth, and the fourth are all called perfect intervals because historically they were tuned perfectly true. Or in other words, those intervals were tuned exact so that they were harmonically accurate. The major intervals use a capital M, and they are a bit more consonant than the minor intervals, which use a lowercase m, which are a bit more dissonant. We also observe that when we double the frequency of any particular note, we produce one octave interval. And every time we double that, we get a new note, but it is a similar note in terms of its characteristics. And those characteristics lead those notes to be given the same note name. So if our lowest note here is given the name of C, then the second harmonic would also be the same note, the note C. The fourth harmonic would be double the second harmonic, and it would also be C. Doubling the fourth harmonic would give us the eighth harmonic, also the note value of C. And we're going to observe now, or Larry's going to show us how we can observe these harmonics to get better understanding of consonance and dissonance.
Thanks, John. So we seek a way to visualize these and look at these harmonics in a way that makes sense visually and also mathematically. So we first thought of maybe a stick with marks representing the harmonics that are equally spaced. Any doubling of a harmonic number gives an octave. But as you can see here, the octaves are getting wider and wider as we go from 1 to 2, and then 2 to 4, 4 to 8, etc. That's not actually how we perceive octaves, so we thought maybe we better think of another way to represent these. Then it dawned on us, maybe we could use a logarithmic stick. These are the same harmonics, but they're not spaced equally. They're logarithmically spaced. And now you see that the doublings, the octaves, are all the same size. Whether it's from 1 to 2, 2 to 4, 4 to 8, or 3 to 6, or even 7 to 14. Those are all octaves that are the same size. And frankly, that's actually how we perceive in our ears, how we perceive octaves. Well, once we did octaves, we thought, can we do that other ratio, that 3 to 2 ratio, the perfect fifth ratio as well? Notice that once we're on the logarithmic sticks here with those harmonics separated that way, then all of the perfect fifth ratios are also the same size. So 3 to 2 and 6 to 4, and any of these others you see with these braces here, 15 to 10, those all reduce to a ratio of 3 to 2. Any frequency ratio of 3 to 2 produces an interval of a perfect fifth. Well, a perfect fourth would be a 4 to 3 ratio. So there's a few things going on here in this slide. Up in the upper right, you see a little keyboard, an octave's worth, with a perfect fifth interval with the purple dots, and then a perfect fourth interval on top of that. On the stick in the middle of the diagram, you see a perfect fifth, where the 3 and the 2 harmonics are labeled, and a perfect fourth interval from the 4 to the 3, and you see that if you put them next to each other, it does indeed add up to a perfect eighth, or an octave. When we have two intervals that add up together to give a full octave, we call them inversions of each other. So a perfect fifth inverted is a perfect fourth, and vice versa. If you look at the algebra below that, you see the 3 to 2 and the 4 to 3. That's the perfect fifth and the perfect fourth. Notice that the 3's cancel, giving you the ratio of 2 to 1, which is the octave, as we said. Here we have two different harmonic series on logarithmic sticks, one shown in blue and the other in red. The fundamental of the red harmonic series is displaced an octave from the blue series. That is, the fundamental of the red series corresponds to the second harmonic of the blue series, which is an octave higher than the blue fundamental. This juxtaposition allows us to show, again, that a perfect fifth plus a perfect fourth is equal to an octave. You can see right here the perfect fifth, the perfect fourth adds up to an octave again. And if you look a little bit more over to the right here, you can see that a major third and a minor third add up to a perfect fifth. Well, does that work on the keyboard? Does that work on the stick? Does that work with the algebra? Yeah, it does. A major third from, say, C to E, and then a minor third from E to G gives you a perfect fifth. And you see that on the stick and also in the algebra below. This time it's not threes that are canceling, it's the fives that cancel, leaving you with a reduced ratio of 3 to 2. Now, what happens if you wanted to find out the difference between two intervals? What if you wanted to know what a perfect fifth minus a perfect fourth would be? Or maybe you could say, what would need to be added to a perfect fourth in order to produce a perfect fifth? For that, for the difference, we actually need to divide ratios rather than multiply the ratios. And to divide, we invert and multiply. In this case, you can see once we invert to multiply, the threes will not cancel, and they both give us the 9 in the numerator. So the ratio of 9 to 8 is the difference between a perfect fifth and a perfect fourth. We call that a major second. And look at the stick. Can you see harmonic number 9 and harmonic number 8? It's labeled as a major second between those two harmonics. There's some other named intervals that you may have heard of. A major sixth is a ratio of 5 to 3, a minor sixth, 8 to 5, and so on. Now, a big consideration in music is whether things sound good. And when things sound really, really great, we use the word consonant intervals. And if they don't sound so wonderful, so homey, maybe they have a little harshness or edge to them, we call them dissonant. Can we find out about those two concepts with our cool logarithmic sticks? Well, you've seen this set of sticks before, but now the point is that many of the higher harmonics match up between these two harmonic series. In fact, all of the red harmonics match up with some blue harmonic. This octave is the most consonant interval. So consonant, in fact, that we even give the two notes the same letter name and think of them as variations of the same note. As John said, if the blue harmonic series is based on a C, then the red one is a C an octave above. They both would be called Cs. That's what it sounds like. Very, very consonant interval. Now, we've got two more sets of sticks here. This time, in the upper set of sticks, the red is only displaced by a perfect fifth. Notice that still many of the harmonics do match up with blue harmonics. That means that this is also a very consonant interval. Not quite as consonant as the octave, but maybe the second most consonant interval is a perfect fifth. Here's what it sounds like. The bottom set of sticks, the red stick is only a major second displaced from the blue harmonic series. If you sound those two together, I want you to notice two things about the sticks, about the lines on the sticks. First of all, notice that not very many of the harmonics are matching up. They're not lining up with the blue and the red together. That's important. Second thing, though, also important, notice that even though they don't line up exactly, they tend to line up almost way more often than they did in the upper set of sticks. So these almost matchups actually produce beats and produce dissonance. So this interval, the major second, is thought of as a more dissonant interval. And that's what it sounds like. Well, we'd like to build some scales. How do we use these, create a sequence of tones that we can use to compose and play music? Let's start with that consonant interval, the P5. And let's look at the circle of fifths that many musicians are in love with, or maybe a love-hate relationship with. This circle of fifths as you go from C to G to D to A around the circle. Pay close attention to that for a minute, how many there are. There are 12 fifths all the way around the circle. Remember that. And on the right, we have a little spinner that shows that you can take those 7 of those fifths together and create a regular diatonic scale using the fifths in the order shown. And that little spinner could spin. Right now, it's rooted on the key of C with an arrow, but you could dial that thing around and start with some other letter name as the root or tonic of the scale and create any diatonic scale in any key just by rotating that around. Well, that's great, but if life were only so simple, we want to build a scale and we want to do it on this constant interval, the fifth. We are going to do that by recalling our friend Pythagoras from ancient Greece, and he did this, build a scale on those perfect fifths. If we don't stop at the 7 perfect fifths of the diatonic scale, but actually keep going around the circle of fifths until we've used all 12 of them, then we have in fact created the chromatic scale, the 12-tone chromatic scale. What I'd like you to notice is that we have the 12 fifths in the upper grand staff here. You can see them all labeled in the middle, and then the note names all the way up. On the bottom staff, we have just octaves. They're all Cs. Ratios of 2 to 1, but they're all in the same pitch class. They're all Cs. What we want you to notice is that if you start on the same bottom note, that way low, low C, go up 12 fifths, you get to a very high B sharp. If you go up 7 octaves, you get to a very high C. B sharp, C, same note, right, on the piano. Well, that's really cool, except it's not, because they're not exactly the same. That 3/2 to the 12th power is not exactly the same as 2 to the 7th power. The mathematical reason is that no power of one prime number can ever equal any power of another prime number. This is significant. This niggling little difference, called the Pythagorean comma, and others to come, demonstrate that choices will have to be made and adjustments will have to be made. That B sharp is just a little bit higher than that high C. If we just do 4 of them, 4 of the perfect fifths, 3/2 to the 4th power, and then divide by 2 a couple of times to bring it back into the same octave, we get what Pythagoras would have come up with as a major third interval. 3/2 to the 4th power divided by 4 gives us the 1.2656. That's a Pythagorean major third, but it's not exactly the major third we talked about earlier, the one on the logarithmic stick, the one that has the ratio of 5 to 4. It's close. 1.2656 is mighty close to 1.25, but there's just this little difference. That means we're going to have to make some adjustments. So we keep exploring. We say, hey, maybe we can make those thirds sound a little bit more pure or true. What can we do about that? This is called the just tuning, and it uses more of these intervals of small whole numbers that you see on the stick. And we can make chords out of these. You've sort of seen this diagram before, but notice that if you start on that C right there, then a major third above that and a minor third above that will produce a major chord. These are just major chords, not a Pythagorean major chord. So these frequency ratios will be in the ratio of 6 to 5 to 4. That's a major chord. You may have recognized that, but it may not be the major chord you can play on your piano at home. Here's what a major chord would look like on the logarithmic stick. This doesn't require us to pick any particular note as the root of the chord. This would apply to any root that you want. You pick whatever key you want that to be, and that's it. You go up a major third, you go up a minor third. There's your major chord with the ratio of 6 to 5 to 4. Notice that the root of the chord, the bottom note of the chord, is not this number clear over here at the 1. That would be actually 2 octaves lower, and that's not what we're talking about. We're not thinking of these 3 notes as simply harmonics on that fundamental 2 octaves lower. We're actually considering these to be 3 separate notes played together as a chord. If you go to the flatted 7th degree of the double flat it a little bit, you can create a tetrachord, a 4-note chord that's called the barbershop 7th chord. And you can see that the ratios using those harmonics, 7, 6, 5, and 4, are very consonant, very nice together. And I'm sure you'd like to hear what that sounds like. Yeah, there's a barbershop 7th chord. Let's hear that one more time. Beautiful. And that's what it looks like on the logarithmic stick with those same ratios. Well, thirds again, 5/4 times 5. It looks on the keyboard like it should add up to an octave if you have 3 thirds. But if you do the math, 1.953 is not exactly equal to 2. So again, we're confronted with this dilemma. We're going to have to make some adjustments. We call those temperaments. We have the Pythagorean tuning and the just tuning, in which some chords in some keys sound absolutely wonderful in those tunings. But other chords in other keys actually sound really bad, terrible in fact. So we try to adjust things and make some compromises. Over the centuries, people have come up with many different temperaments that please their ear. Here's some examples of different temperaments that people have come up with over the past 3 or 4 centuries. A person you've heard of, Johann Sebastian Bach, specifically picked one temperament and wrote 48 preludes and fugues in all the different keys to demonstrate that if you used a well temperament, not any old temperament, you could make things sound good in all of the keys. That's exactly what well temperaments do. They allow you to use all of the keys on the keyboard. If you take that to an extreme and temper until you get to here, you have what we call an equal tempered. This might be the most tempered or makes the most compromises. Nothing sounds perfect in an equal temperament, but everything sounds okay, reasonable. I would like to point out that contrary to widely held belief, Bach was not advocating for this equal temperament. This is a very common misconception. It's in a lot of textbooks and dictionaries, music dictionaries. Bach was not advocating for equal temperament. He used well temperaments, and well does not equal equal. In fact, we were really unable to have a consistent system of tuning pianos to the equal temperament until 100 years ago. So before that, it was dicey if you wanted an equal temperament, and most people didn't. What does the equal temperament do? It makes everything equal. It makes everything the same. It means we need to divide up that octave, that ratio of 2 to 1, into 12 equal half steps. 12 equal. How are you going to divide an interval of 2, an octave, into 12 equal half steps? Well, you can't do it linearly, we've seen. We must do it logarithmically. And so here is the formula for a half-step ratio, 1.059. If you play those two frequencies together, yeah, that's a half step. The good thing about that is if you take that number and raise it to the 12th power, it gives you back 2, which you expect. In other words, 12 half steps, 12 equal tempered half steps, does indeed give you an octave as you expect. Notice that 5 of these half steps gives you a perfect 4th on the keyboard. 7 of these half steps is a perfect 5th on the keyboard. Furthermore, we divide each semitone into 100 cents, just like a dollar. And if we want to talk about the distance between two frequencies in cents, we have this nice little formula, which, notice, uses logarithms. See, all this is starting to fit together. Distance between two frequencies in cents has a logarithm in it. And so let's apply this once just for an example to see how this works. If we take two frequencies that are in fact an octave apart, so the frequency B in the numerator is 2 times the frequency A in the denominator, then the parentheses is just 2, and the log base 2 of 2 is 1, and so we see that there are 1,200 cents in an octave. How about that 5th? How many half steps were there in a perfect 5th? There's 7 of them. 12th through to 2 to the 7th power. Ooh, look how close that is to 1.5. But not exactly the same. However, the perfect 4th is off just enough the other way that if you have a perfect 5th, that's 7 of these half steps, and a perfect 4th, that's 5 of these half steps, and you do the math on those, guess what? You get a perfect octave. It does give you the ratio of 2. And if you do it in cents instead of 12th roots of 2, 700 cents is a perfect 5th, 500 cents is a perfect 4th, adds up to 1,200 cents. Now, a Pythagorean or just 5th would not be a tempered 5th. We're distinguishing between these 5ths now. A tempered fifth is not the same as a Pythagorean fifth. So here are the cent values for a Pythagorean or perfect fifth and a perfect fourth and the major second interval of 9/8 that we talked about before. But guess what? If you do the cents arithmetic on a perfect fifth as 702 cents and a perfect fourth at 498 cents, it adds up to 1,200 cents. And if you subtract 702 cents minus 498 cents, you get a major second as we expect. So we have these three tunings we've talked about here today. The round 100 numbers on the top correspond exactly to the blue lines. Those are the equal tempered lines. The other intervals on the tunings and the colors, so you can see the color legend at the bottom, are not the same. They're different. But do notice the symmetry. Do notice the inversions, that a perfect fourth plus a perfect fifth equals an octave, or a major third plus a minor sixth. Let's look at that one really fast. A major third plus a minor sixth gives you the full stick width, the whole octave. And that's true whether you look at the red lines or the blue lines or the green lines. Those intervals, those inversions always work. So why do we use equal temperament today? Does it sound better? We made improvements? Is this, the progress of the state of music? Not really. Equal temperament actually doesn't necessarily sound better. We have instruments that have fixed pitches. Here's one that's pretty famous, and it's really hard to retune that to make it have different pitches. And here's a fixed pitch clavier, maybe very much like Bach's, who knows. We also have some instruments that are non-fixed pitch, where they can play any frequency, any pitch they want to just by moving their fingers a little bit, or moving their vocal cords a little bit. These are also non-fixed pitch instruments. This allows them to not only hit the notes on the piano, but do the red and the green notes we just saw on that stick. So with that idea of fixed pitch instruments being kind of dictating where we go, and non-fixed pitch instruments giving us more flexibility, I'm going to turn the time back over to John for another discussion.
So what we saw with those Pythagorean temperaments and the just intonation is that the different intervals are different sizes. And over time, as composers wrote music for those, they discovered that different keys had different moods or different feelings. If a composer wanted to write something that sounded reverent or quiet or peaceful, serene, they would have chosen a specific key to write in. And again, depending on what mood they wanted to portray with their music, they would choose a specific key to write in. And what you notice here is that not every key is represented, because with other temperament systems, not every key sounded good. You couldn't make good music in those keys on a fixed pitch instrument unless you retuned the instrument to that specific key. We're going to listen to a few sound clips here showing the differences between equal temperament, Pythagorean, and just intonation. So in blue at the top we have two sticks. The first stick at the very top represents the position of equal tempered notes. Now if a keyboard instrument or a fixed pitch instrument is tuned with those notes in mind, and we attempt to play in a different key, it will not matter in the slightest. Those notes will all be in alignment. It will be exactly where we expect them to be. In the middle picture, we have Pythagorean tuning. The top line of Pythagorean tuning shows where the notes would be tuned at in a specific key, but if we attempted to play in a key 5 steps above that tone, not every note would be exactly as we expected it to be. Most of them in this case are. There's just one little problem here where that note is going to sound sharper than it would, or what we would expect it to sound like. At the bottom scale, we have the just intonation. Again, the top shows what the keyboard would be tuned at, and the bottom would show what we would expect to hear if we played in a key that was 5 tones above what the instrument was tuned in. Here is a brief clip of Bach's Prelude in C, the first of his 48 preludes and fugues from the Well-Tempered Clavier. This is played on a keyboard with Pythagorean tuning tuned in the key of C, so tuned to the key that the music is written. That did not sound terrible. That sounded pretty pleasant. But what would happen if we attempted to play the same piece using the same notes, but if the instrument had been tuned to a different key, specifically tuned to the key of A flat? For most of us, that may not sound like much of a difference. It is very subtle. Here's what just intonation would sound like, tuned on the key of C. Again, a very pleasant sound. The notes sound like they go well together. But what would happen if we had our keyboard tuned to the key of G flat, and we attempted to play a piece of music in the key of C? Now, this is what my children would call cringe. You may want to hold on to something as you listen to this. Make it stop, please. That was awful. Now again, that's not to say that the key of G flat is bad inherently. You would just have to play music in that key on an instrument tuned specifically to that key. And retuning a keyboard instrument is not a trivial thing. It takes work and a lot of time. Here is equal temperament. This is what we are most familiar with today. This again sounds very pleasant, very familiar. Although this is not necessarily what you would have heard in Bach's time, because again, Bach did not compose or write music for equal tempered keyboards. He preferred well tempering. Not only that, Bach did not see the piano invented until halfway through his life. Bach was very famous for actually tuning his own keyboards anytime he performed on them. One particular tuning that he liked to use, or something similar to what he used, was the Werkmeister tuning. And this, in our opinion, is probably the best sounding of all of these. So with Bach's idea, you could compose in any key on a well-tempered keyboard, and it would still sound okay. You didn't have to avoid any particular keys in your composition. There are still plenty of music ensembles today that produce period music or play music that was written in 200 to 300 years ago. They not only use period instruments, but they use different tunings in the way that they play. They do not use equal temperament. As we noted, there is a very circular nature or a periodic nature to music. We go from the note A to the note G and then we repeat. So we can represent all of these musical ideas on a circular scale. We'll call this the circular pitch class space. In the equal tempered system, all of our pitches are equally spaced out in terms of 100 cents apart from each other. But rather than looking at the spacing of the equal tempered scale, we could compare the spacing of the Pythagorean or just scales. And to do that, we're going to look back at our logarithmic stick here. We're going to take this stick and rotate it around to make a complete circle. But we're going to take each individual octave and rotate it around to its own circle. So the first octave from the first to the second harmonic will be rotated into its own circle. From the second to the fourth will be rotated into its own circle. From the fourth to the eighth will be its own circle, and so on. This produces the picture on the left of the multi-ring harmonics. Again, the inner circle is that fundamental to the second harmonic, one full rotation. That second harmonic is the same note as the fundamental. If we go around to the third harmonic and then to the fourth, we go through one more octave. And every time we do, the alignment of the harmonics gives us different pitch classes. So these notes here, 1, 2, 4, 8, 16, are all the same note name. Over here from 3 to 6 to 12, those are all the same note name. The harmonics align in this correct note names. We can condense all of those rings down into one, showing the position of all of those harmonics together on a single ring. We can also show consonance and dissonance using these multi-ring and single-ring pictures by overlaying a second circle. So in blue we have one particular note, and overlaying it in red is another one, but rotated through a perfect fifth. We again observe the overlap of the harmonics in this particular area, and where they overlap, they give us the 3:2 perfect fifth ratio. Everywhere else we get overlap is in the 3:2 ratio, and the same can be observed with the single rings. One challenge that this multi-ring picture has is that when you rotate the rings, anytime a harmonic reaches the 12 o'clock position, it needs to be bumped up to the next ring. It is in a new octave. So here we observe the major second, also using the multi-ring and single ring with one rotated around the other. Again, we observe that not as many harmonics overlap, but when they do overlap, they are in the 9:8 ratio. We also observe the other points that are close together, such as here, and those harmonics being close but not equal helps produce some of the dissonance of that sound. So the major chords all are going to sound very different in each of these different tuning systems. The Pythagorean major chord makes emphasis of the perfect fifth. The just major chord not only takes that fifth, but makes the third also sound better. So the just major chord is ultimately much more pure than the Pythagorean major chord. The equal tempered major chord, not as good, because none of them are at the perfect ratio. With our circles, we can go through the circle of fifths, every time increasing to get to the next note on the circle. What you observe on the right side is that we have the equal tempered fifths drawn with solid lines and the Pythagorean fifths drawn in the dashed lines. The Pythagorean fifths are not equal to the equal tempered fifths. And so the time we make our way back around one full cycle back to the starting note of C, we are significantly far away from what we were expecting, and that distance is, again, the Pythagorean comma. As we represent the sticks and the different tuning systems on a circle, we again note the symmetry of all of the different intervals. Across the 12 o'clock position, we do get a great deal of symmetry, a lot of beauty there in mathematics. There is, of course, the 600 tritone position, but we do not talk about that little devil because, never mind. Other places, we of course do see the symmetry. Likewise with the sticks, we can show what we would expect to see and what we actually hear if we play in different temperaments in different keys from the tuning. So we have two rings here, two circles. The outside circle represents the frequencies that a Pythagorean instrument would be tuned at. And if we played at the 7th scale degree above that, not all of the notes would be as expected. Most of them would be, but the 6th scale degree on that keyboard would be a little bit different. It would be flatter than what we would expect. So playing in a different key in Pythagorean temperament from what the instrument is tuned at may not sound the same. The same is observed here with the just tuning. The outer key may represent how the instrument is tuned, but if we play in a different key, in this case 5 scale degrees above that, many more notes are going to sound different than what we were expecting them to sound like. With equal temperament, it doesn't matter in the slightest. We can play in any key, no matter what the instrument is tuned at, every key will sound equally the same for each piece of music. Rather than circles, we can make one additional step further, and that is to use a spiral. By taking the linearly spaced sticks and wrapping it around, not forming a complete circle, but forming a logarithmic spiral, we still see the pitch classes lining up. Here we have highlighted the 5, 10, and 20 pitch class, all in the same position from the center of that spiral. Not only this, we observe that the distance from the center of the spiral doubles each time we get to a new arm as we rotate around the spiral. The distance around the spiral always doubles as well as we go around through an octave ratio. So what we observe with all of this is that we have to make compromises. If we want to play on a keyboard instrument in all different keys, we have to compromise in our tunings so that they are not all equally the same. So, again, we have different moods out of all of this in Pythagorean and just intonation. With equal temperament, we lose those moods because it doesn't matter which key you play in, we get the same overall sound. There is no difference with equal temperament. So you might say that there is a distinct disadvantage with equal temperament that we do not see with some of these others. I'll take over.
We just finishing up here. It's time to end. These are just a refresher that we're demonstrating and visualizing these mathematical concepts on the sticks and the circles, and that it helps your understanding of music. Music is the mathematics of the soul, and mathematics is the music of the mind. So our final concluding slide is that an understanding of math can enhance our appreciation and enjoyment of music. Thank you very much.
Thank you for coming today. It is 1:20. If some of you have to leave to get to your next class, you're excused. But if some of you would like to stay and ask questions of Professor Smith and Tyler, we invite you to do so. Come to the stage. Thanks.